We say a discrete sample space is a set that's countable. Intuitively, you got to know those definitions intuitively too. So when they say, well, my students don't only know it intuitively, that's important though. You need to have some intuition. So it's like you can put your finger on each one of the dots in the set. So you can obviously think, can you give me examples where the sample space is countable?
So if you had a set that's like a set with A, B, and C, I mean that
Three
those
things in it.
elements are
Flipping a coin. So I talk about examples. Tell me things that I can actually touch and see, right? So think of like a flipping coin, how about rolling a die, deck of cards, all of those. Like if I have a deck of cards and I pull one from the deck of cards, the sample space I get are all the faces of the cards, right? And that's a discrete sample space because they're all finite. So I talk about good examples and bad examples. I'm gonna actually grade you on the quality of your example. Your example should be good for you, so you should understand something from it. What's missing in all those examples? Can a countable set be infinite? Yes. So the first question I had when I read this was probably not the same question you had. The first question I had was, well, what example of a sample space is infinite and countable? I mean, infinite and countable. I can think of things that are real numbers, because that's distributions. You're talking about distributions there. I'm thinking of something that's simple, countable, but infinite. I'll show you an example in a second because I did see one. So if S is discrete, an event is a subset of S, at least in your book. So when someone says event, you think set, and subset of the big sample space. When someone says, so far have we done any weird examples? Sample space, it's a set. So far you have those things, you should have those things straight in your mind, put them on the table, and forevermore you know what it is. Okay, accountably infinite sample space. So suppose you have a roulette wheel where you're spinning it and it has 0, 0, 0, 1, 2, all the way up to 36. Those are the numbers on it. So let S be the sample space of the set of sequences you may encounter until you reach the number 36. So what are the possibilities? Well, I could roll 36. I could actually spin 36 on my first one, right? So that's 1. I could do 0 first, get 0 first and then 36. I could get 0, 0, 0 and then 36. And then I could get 0 n number of times and get 36. So there's a whole bunch of different things I could get, but they're countable. I can tag them all possibilities, to something in n. There's an infinite number in here, but I can list them out. If you can list them out, it's countable. I needed to see that, because as soon as I read the definition, I need to see an example like that. Okay, are there any questions? When I say that this is a way of thinking, it's when I first went to Georgia Tech, because nobody at University of Montana made me do anything. I guess I'm putting this on YouTube. They didn't make me do anything. Top 10 party school. Yeah. So when I went to Georgia Tech, they made me do it in a bad way, like the Thayer method on steroids. And so I remember just like not understanding what they're asking me for. And then they taught me how to think this way. They forced me to think this way. And another person who went to Georgia Tech that talked about this was Colonel Laporte's dad. Talked about how it feels like to be in one of those classes at the graduate level, because you're like, oh boy, I'm not an undergrad anymore. I wish I had this class actually before I took measure theory. So if I wrote this in symbols, if somebody tells me E is an event, this is what I know about E. E is a subset of S. And I also know the definition of E. E to be is a subset of X. It means that every member of E is also a member of S. That's the definition. So all of those things are straight in my mind. All right, here we go to probability. So I'm going to revise what you thought of probability. Is it a number? Is it a distribution? Well, here we go. If S is a sample space, for you, you're using what's called the power sets of a sample space. That means you're looking at all subsets of that sample space. And they subvert that in the later discussion in your book when they go to continuous stuff. And maybe I'll mention it when the time comes, how to think of it. But it's, for example, if you have tails and heads, what are all the subsets? Let's just list them out. If I have the sample space is tails and heads, what are the possible subsets I could get? You haven't answered anything. Should I answer something?
With two flips, maybe?
This is just one flip. I got one coin, flipped it.
You either get tails or heads.
Right, that's the sample space. Those are the all possible outcomes for the sample space. What else could I have as an event? A subset of this. Can you think of a subset of this? Just tails. So they list it as these tails. What else? Now you can answer this one, right? You could get heads. You could get the whole thing. And you could also get empty sets always there. They don't say that, but in power sets, empty set is always there. So I have 2 things in here, and I have 4 things in the power sets. So quick calculation, you can tell me by the end of class, somebody, if I had n things in there, how many power sets am I going to get? 2 to the n. Right. It's combinatorics. Okay, so probability is a function. The domain are the power sets of the sample space. The range is 0, 1. So that's what this means. Probability is a function. My inputs into the function are sets that are power sets of the sample space. The outputs are numbers between 0 and 1. How many of you put function on your paper at the beginning? We already learned something, right? You put function? The first property is that P of A has to be 0 for all A that belong to the power set, so any subset of the sample space. The probability of the whole sample space is 1. And the last property is that if I have a sequence of sets, and they have nothing in common, so A intersect B is equal to the empty set, they don't share any elements, then the probability of their union is their sum. Split it up this way. Literally, my measure theory professor gave this definition and something like the power set definition, and for the rest of, I think, the next 2 weeks, he was proving things using those 2 things. I didn't know what was going on. I was so miserable. Okay? Not okay? Got a question? Let me know if you have a question.
So this joint means there's no intersection.
Hmm?
This joint, that means there's no intersection.
Right, this joint means, I don't have any markers in here. This joint means that AI does not equal, AI intersect AJ is equal to the empty set for any AI or J. No intersection. Anything else? Hopefully Dr. Kurtz won't listen to my YouTube videos. He'll get mad. Type, it's a function. Probability is a function. So when I taught 376, I think Marina is the only one that had me for 376. I would struggle in there because I would want formal definitions for things. What is this? I need to know what that's the failing of a mathematician. They can't sometimes go into an applied class or an engineering class and survive there because they're just tangled up with, what is this, does this mean? And we were actually doing problems in there without knowing the full meaning. So that one was a tough class. So the pure mathematicians in the department asked me, why do you think 376 is a tough class? And for me, it was, and I think for you, it will be too. Because we did a lot of stuff in there that was just not formalized. Okay, so we're almost done. I'm going to stop here. I have some problems that I put on the end of here that I was going to have you try out, which they're just sample problems. They're very similar to the problems that you have as computational problems on the first homework, at least the first part of it. The last part of it is the spinner type problems, so they're a little bit more messy. But the first ones are this. And those solutions are on here too. So, and you can show me what you got if you got something different. This should be just warm up. Those problems should be warm up. So I recommend you look at them at least before you start your homework and you can see it. But your book also uses this idea. You have everything, the whole sample space is supposed to be 1. I can split up each of that separately. And if it's a balanced, fair coin, then I know that each one of these are a half. So then I have everything I need to know. They call that a method, but it's not really a method. It's kind of logic. You're just using the definition.